Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
But so we are very fortunate to have Rhea coming from West Virginia, and she's going to talk about rehabilitation using Kinect in the rehabilitation process. Thank you.
Thanks. Thanks so much for having me here. So I do live on the other side of the country right now, but I actually did my undergraduate work in Washington, just down the road in Tacoma. So it's good to be back to my pseudo home, or what was my home for 5 years, not too long ago. So hopefully I can kind of keep everybody's attention. I know we may all be in that kind of post-lunch lag right now, but I really want to share with you some of the research we've been doing, and in particular the research I've been doing for my thesis, which is really directed at using the Kinect for two purposes in stroke motor improvements. And that is really first the assessment of stroke patients and their initial motor deficits and kind of tracking their improvements, or in some cases decline over time, but then also using the Kinect in one step further and kind of as a rehabilitation device. So just to give you an idea, since I think most of you are kind of familiar faces to each other, and you probably all know what the UW campus looks like, but just to give you an idea, I am at West Virginia University. I am technically in the Center for Neuroscience, although we also are kind of interdisciplinary with the physical therapy department. So that nice glass building is kind of where I call my home right now. And we're located within a subdivision of the Center for Neuroscience, which is actually a clinical translational stroke center. This center was developed not too long ago, but we span everything from human clinical translational work all the way down to more molecular and genetic mechanisms of stroke. So we have a really nice breadth and depth of research groups that are kind of all involved in this stroke center. We like to say that we have the opportunity to study stroke patients because we are one of the highest states at risk and incidence of stroke, which gives us a great patient population to pull from. So good opportunity for us, maybe not a great opportunity for some of the people who live there. But in either case, West Virginia University Hospital, which we are actually fortunate enough to be physically attached to, so it makes it really easy to get access to both patients, neurologists, and clinicians. Ruby Hospital, which is our West Virginia University Hospital, is the only stroke certified center in West Virginia. So anytime a patient has a stroke in West Virginia, is upon entry to the emergency department in whatever county or city local hospital they have, if somebody thinks they're having a stroke, they're immediately life flighted to our hospital. So again, huge population of patients for us to pull from, which has really allowed the research that we're conducting to really be possible, since we do have this great breadth of patient population. We're also really fortunate that we have great access to our neurologists and physical therapists. So we have these monthly meetings. They're always available to help and kind of talk and collaborate with me and my PI as well whenever we need them. But this has really enabled us to kind of drive our research to meet clinical needs. We have no interest in developing another tool that clinicians and physical therapists have no interest or no need to use, right? Because it wastes everybody's time and money, and there's just really no point in it. So to give you an idea, just kind of a basic overview of what our lab does, I'm a graduate student in the Neuroengineering and Rehabilitation Lab. And in general, our focus is kind of twofold. One, to understand the underlying mechanisms of motor control. So how do we go from wanting to make a movement to our central and peripheral nervous systems working together to integrate, develop a plan, and then carry out that plan in an effective action. We're also really interested in looking at how these mechanisms change with neurological injury. So what are kind of the underlying mechanisms that cause somebody who's had a stroke to kind of present with these typical phenotypes we see in these motor impairments we see? And we'd like to take what we learn from both healthy individuals and those who have suffered from a stroke and kind of combine that scientific evidence to really build and help improve rehabilitation practices. And that's really what drives the majority of research that goes on in our lab. So how do we do this? I'm sure most of you are familiar with most of these tools, but motion to capture equipment we use in the lab, we use an active LED system, which is our phase-space impulse system. So we have 18 cameras set up in our lab. We can put anywhere from 36 to 48 LEDs on an individual to get full body motion capture. Fantastic temporal resolution, so we can record at 480 frames a second, and we get sub-millimeter precision spatial accuracy. We also obviously use the Kinect, which is a lot of the research I'm going to be talking about today. For electromyography or muscle activity recordings, we have two systems. We use our Delcy system, which is a wireless system, when we want to look at patients kind of interacting in an environment or moving around a space. We also have our Motion Lab system, which is a wired system. The benefit to this system, even though it is a little bit more cumbersome, is the fact that we can synchronize everything incredibly well. So between our kinematic and our dynamic information we're getting, we have fantastic synchronization. We can also synchronize it with our transcranial magnetic stimulator that we use. So for those of you who are not familiar, TMS, transcranial magnetic stimulation, basically takes advantage of magnetic fields, and when you pulse this thing, it activates a portion of the cortex over which you're hovering. We have two types of coils. The coil I have here in the picture is more of a V-shaped coil, so it actually is shaped like this, and what that allows us to do is penetrate deeper into the sulci, to the areas of the motor cortex that are more in control of your lower legs. We also have a flat coil, which is more shaped like this, and that can stimulate the more peripheral areas of the motor cortex so we can target upper body function. The beauty of the TMS is it allows us to really look at how the motor cortex is directly interacting with specific movements. So as somebody's moving, we can use the TMS to stimulate the cortical spinal tract and really look at the involvement there of the motor cortex in the movement. We also, our kind of new fancy piece of equipment we've been kind of integrating into our lab is we recently got a Vertex split belt treadmill. This is integrated with AMTI force plates, so we get fantastic force data while being able to manipulate these belts individually of each other for speed. So we're doing a lot of studies looking at kind of perception of difference in speed, speed difference between the two legs. And again, we can kind of combine all these or kind of attempt to, as synchronizedly as possible, record all of this data at once. We also use the Oculus Rift, which is a 3D goggle setup. So it actually kind of looks like snowboarding goggles that are all enclosed. And this is great for immersive 3D environments. We use the Vizard system as kind of our platform to build these virtual environments. So what a lot of our experiments involve is having individuals reach to different targets. And so the way we do that, instead of having to have this big contraption in front of them, is we actually project the targets in 3D space. The beauty and kind of what we do is once we put the LEDs on somebody's arm, now they can see their arm actually move in space in that 3D helmet. So we kind of have this representation stick figure, so they actually feel like they're really touching and reaching to the targets, which I think makes it a lot more realistic. I probably don't have to go over this. Hearing some of the talks today, I think we're pretty all comfortable with what motor impairment is, but again, it's something just important to keep in mind when we're designing both assessment and rehabilitation protocols. We have to understand that motor impairments are very variable, so they can affect just one limb or multiple limbs, and the etiology of these diseases can really be different. So even though two individuals may be presenting with similar motor deficits, how those motor deficits are really arising in the individual can be dramatically different, and I think that's really important to understand when you're trying to treat those motor impairments. Okay, so since I'm going to be talking about stroke, I just want to give you a little bit of background on some of the statistics as well as what a stroke is. So this is not just a problem in America. Globally, there's roughly 15 million individuals who will suffer from a stroke each year. It's the second leading cause of death and disability globally. When we look at it within the United States, there's roughly 800,000 strokes that occur each year. It's become the leading cause of death and the leading cause of adult disability. And it's projected or estimated that we spend roughly $74 billion a year treating both the acute and long-term effects of stroke. So obviously this is a pretty pertinent problem right now. So for those of you who don't know, although probably comfortable saying most of us do know here what a stroke is, but we can kind of think of it as a heart attack of the brain. So specifically there's two types of strokes. We see ischemic and hemorrhagic. Ischemic strokes are far more prevalent. They cover about 87% of all strokes. And this is where there is a blockage of a blood vessel in the brain. So again, when you develop a blood clot somewhere in your body and it's thrown or carried to a portion of the brain and it cuts off a portion of blood supply to an area of the cortex. Hemorrhagic strokes, on the other hand, are slightly less common but can be as devastating as an ischemic. And this is a rupture of a blood vessel which then leaks the blood into the surrounding area of the tissue. Size and location of strokes obviously vary widely, but size does not always mean severity. So you can have a very small stroke, but if it's in a really crucial part of your cortex, it could impact you just as severely as somebody who's had a very large or broad stroke. One important thing that we talk a lot about as far as kind of initial assessment or tracking patients in the more acute phases of the stroke, so the first 48, 72 hours after stroke, is the difference between core and penumbra tissue. So a core of a stroke is really the immediate area or the immediate cells that have been damaged or killed off by that stroke. The penumbra is more of this surrounding area here. And this tissue is kind of the at-risk tissue for becoming kind of enveloped into that core area. So a lot of the acute treatments that are kind of projected or researched for stroke, acute stroke treatment really focus on salvaging as much of that penumbra tissue as possible and really limiting the size of that core. Because in the long term, the less amount of tissue you can lose, the better prognosis and the better outcome the patient will have. So acute kind of treatment or assessment of a stroke, again, when somebody comes into a emergency room and is presenting with stroke-like symptoms, they may have a very basic neurological exam, and if a neurologist or clinician thinks they are in fact having a stroke, the most typical second step will be a radiological assessment. At West Virginia University in particular, we start with a CT scan, then move on to an MRI scan if it's deemed necessary. And this will really tell you kind of location of the stroke and perhaps severity of the stroke if you can get at that information. To treat a stroke acutely, so once somebody's in the emergency room, you've deemed that they are in fact having a stroke, you kind of have two treatment options as of right now. You can use TPA, tissue plasminogen activator, which is given through an IP injection, travels to the site of the clot, and basically just works to dissolve that clot up and return blood flow to the area. The other thing that's being used right now is a mechanical device. There's several different types, but just to give you an idea, this little cathode is snaked up through a major artery. They basically find the site of the clot and then through either a balloon or a kind of twisting mechanism attach onto the clot, retrieve it, and again the idea is to return blood flow to that area that is lacking blood. So when we talk about initial stroke assessment, one of the things commonly used, again, kind of in the emergency room setting, is the NIH stroke scale. This is a very broad scale. It covers everything from speech and language to ability to swallow to very generalized motor function. So they really just look at upper versus lower extremity function. Doesn't give a lot of motor detail. But this can kind of tell a neurologist maybe where somebody is initially, and they can track it in the 24, 48, 72 hours post-stroke. Now, when we talk about specific deficits associated with a stroke, we kind of have two broad phenotypes that we look at. So we have the spasticity, or this increased muscle tone, and this obviously leads to problems such as being able to grasp an object or release an object, decreases fluidity and motion as well as range of motion. Hemiplegia is the other kind of typical phenotype we see, and this is more of your flaccid paralysis. And as we've talked about earlier, in older adults especially who have this hemiplegia after stroke, this really leads to an increased susceptibility to falls after a stroke. But again, it's important to kind of keep these phenotypes in mind when we're developing both assessments and rehabilitation tools, because certain patients are going to have different levels of kind of general motor impairment right after their stroke. Okay, so when we're talking about initial assessments, a lot of the tools that have kind of been developed to initially assess motor function of a stroke patient really have maybe been developed more for research purposes or research tools to kind of look at effectiveness of a treatment over time. Some of the problems associated with these assessments, sorry that that's cut off there, but it's just the title. Some of the problems associated with these is the fact that they're very wide range as to what they're actually looking at. So some of these assessments focus more on ability to kind of manipulate fine objects, whereas other assessments might look at more broad range functional activities of daily living. Some of the benefits, though, to these assessments is that, again, they can be a really useful research tool. So when we want to look at the effectiveness of a treatment paradigm, we can use one of these assessments to kind of get an initial idea of where the patient's at and then look at their progress over time. The drawbacks to these is the fact that we're really not sure if they're capturing these underlying motor deficits that they have after a stroke. So again, when you're asking a stroke patient to lift a cup and you're measuring their ability to lift the cup, are you really seeing what is underlying that motor deficit, or are you just looking at their ability to lift a cup? Also, the scores, they can sometimes be vague and they're not often used consistently in a clinical setting. So if you're not tracking a patient's progress over time using a kind of standard assessment, how are you really knowing if the treatment or rehabilitation paradigm you're providing that patient is really working? Also, a lot of these assessments can be lengthy and they can be difficult to perform, whether it's due to the size of area you need to perform the assessment or the specific tools you need to perform the assessment. So again, benefits and drawbacks, but our idea is really to kind of meet the needs of both clinicians and patients to develop some sort of assessment and rehabilitation tool that may be better able to kind of characterize some of these underlying motor impairments. So I kind of have the project that we're working on right now broken up into 4 aims. In aims 1 and 2, I'm going to be focusing more on the assessment side of things, whereas aims 3 and 4 are a little bit more geared towards the long-term rehabilitation of these stroke patients. Okay, so the first thing we wanted to do was, again, we need to come up with a tool that's low cost and can be used clinically. As we talked about earlier today, we have these fantastic motion capture systems, but to put them in every clinic seems a little bit not very feasible, and they're very expensive, and the number of personnel and how well the personnel have to be trained to get information out of those systems really can be quite cumbersome. So the idea we kind of had was, okay, well, let's find a better option. Let's find something that's easier to use and is more low cost. Well, the Kinect obviously presents itself well to both of those options. So our first idea was to compare how well the Kinect can capture kinematics compared to a state-of-the-art system. And that was really the first kind of general goal of this first aim. We also wanted to determine if we could use an automated algorithm to actually score a stroke patient's motor ability. So again, this is kind of our face-based system here, active LED system that we use to compare against the Kinect. So what we did is we had 10 stroke patients perform movements that are based on clinical assessments. The movements we had them perform are illustrated down here. And this diagram just kind of shows the actual difference in positioning of the active markers, the LED markers, versus where the Kinect tracks the human body. And we recorded, as we had our stroke patients perform these movements, we recorded them simultaneously with the Kinect and with the face-based system. After we recorded that data, we calculated joint angles of the shoulder, elbow, and wrist, and then we basically compared kinematic or motion capture ability between those two systems. So if we look at the average error between the two motion capture systems, this was across all of our patients in all 10 movements, we see that we get an average difference between the face-based and the Kinect system for shoulder flexion extension of 14%, shoulder abduction adduction of 12%, elbow flexion extension of 2%, and wrist flexion extension of 7%. 14 and 12% may seem maybe on the larger side of things as far as an average difference between the two systems, but what was really more intriguing is the fact that those averages were pretty consistent across all of our patients. The benefit to this is as long as we know that the two systems have an average difference that's fairly consistent, it really shouldn't actually affect the scoring that we did later on with the kinematic data. So again, then we wanted to determine if we could use the face-based and motion capture Kinect systems to automate the scoring of a stroke patient's motor impairment. So in plot A, what we have here along this line, here along the x-axis, are the scores derived from the face-based motion capture system compared to the scores derived from the Kinect system. Again, we had a pretty good linear relationship between the two, suggesting that the two systems, basically the kinematics that we were extracting, were comparable to create this quantitative score we developed. We also then compared the Kinect scores, which is now on the x-axis, to the qualitative scores. These qualitative scores were generated from 30 physical therapy students rating each one of our patients' movements. So we would video record each of our patients, de-identify them by basically blurring out their face, and then we had 30 physical therapy students rate the patient's movements on a 0 to 2 scale. And that's what we used for comparing to our Kinect-based scoring system. Another interesting thing we found from this data was when we look at interclass correlation coefficient, or basically how well the human raters are performing compared to our system, we found that it was usually about an average of 3 human raters that it took to get a comparable score to our computer-based algorithm. So this suggests that perhaps it could provide a more accurate score than 1 or 2 physical therapy students, and maybe it could perform better in a clinical setting. So the second kind of wave of this research then was to determine if we could use this automated algorithm we've developed to really automate a clinical assessment. So for this, we chose the Wolf Motor Function Test. If you're not familiar with it, this consists of roughly 17 movements that are pretty typical of activities of daily living. We did omit 2 movements just for some feasibility purposes. But we had 10 stroke patients perform the Wolf Motor Function Test with both their affected and unaffected limb, and we recorded them while they were moving with the Kinect. Again, we had physical therapy students rate their movements on the 0 to 5 now scale that the Wolf Motor Function Test uses. And then we compared our automated algorithm to the performance of those physical therapy students. So to give you an idea of actually how our algorithm works, what we do is once we've calculated the joint angle data for both the affected and unaffected arm, we use a decomposition analysis. And really what this does is it pulls out the major kind of trends or the major variance in the data. So I'm going to kind of go through this step by step. Hopefully it'll make as much sense as possible. So the solid lines that I have represented in all these graphs are the actual kinematics we recorded from the Kinect. The dashed lines are the reconstructed movement that we get from extracting 2 principal components from the unaffected arm. So what we do is we extract these principal components here, and then we reconstruct the affected arm movement. And then what we use is we use correlation coefficients to quantify how similar, or in some cases how different, that reconstruction was from the original data set. And what that allows us to do is really quantify difference in movement ability between the 2 arms. So in the top plot here, this section here, we have a mildly impaired patient who really didn't have a lot of difference in motor ability between their 2 limbs. This individual would have received a high score on our quantitative algorithm, whereas if you compare it with a more severely impaired patient, you can see here they have pretty little to almost no movement ability in their affected arm. In this patient, the difference between the affected and unaffected limbs would be greater, so they'd get a lower score on our quantitative algorithm. If we look at the overall observations between our quantitative scores, which are now here on the y-axis, and the scores from the physical therapy students, we actually get a surprisingly good relationship between the 2. One thing we did notice, and through talking with some physical therapists and actually talking with Dr. Wolf, who, unbeknownst to him, that test was named after him. He didn't actually develop that test, which was kind of interesting. But what typically happens a lot is we get these floor and ceiling effects here. So if I can get my pointer. So it's really easy to give somebody a 5, which is perfect movement, or a 0 or 1, which is almost no movement. But it's really hard to kind of delineate in between. So what we see is a lot of our patients kind of were given these scores of that averaged out somewhere between 4.5 and 5, but we see a lot bigger difference in our quantitative algorithm. We don't think that that's because the quantitative algorithm isn't working well. We actually think that's because this is based off of kinematic recordings. It's actually picking up some of the minute differences that a human may not be able to detect just through eyesight. The other important consideration for the Wolf Motor Function Test is that there's a time domain associated with it. So all of the patients are recorded on their time to perform each test. So we wanted to make sure that our automated algorithm could also detect onset and offset of movement. And what we did for this was just basically used a kind of simple velocity threshold detection method. Again, we saw a pretty good correlation between that and the time domain found by human physical therapists. So again, those were kind of the 2 assessment-based research tasks that we've taken on. And again, we really want to kind of alleviate some of the cost and time constraints that cause these assessments to not be used on a consistent basis in the clinic. We also want to provide this more quantitative measure for motor impairment, so really kind of make some sort of defining numeric scale, basically, of which you can measure a stroke patient's improvement over time. Okay, so moving away from the assessment side then and getting more into the rehabilitation side, aims 3 and 4 were are much more geared towards looking at long-term rehabilitation using the Kinect. So some of the things we want to address in aims 3 and 4 are to track patients' improvements, but also to improve specific joint angle scores. So right now we'd get 1 score for the patient. We'd actually like to get scores for specific degrees of freedom at each joint. We'd also like to eventually bring this care into patients' home and kind of develop this network for rehabilitation, which I'll get into more in a second. So I'm sure many of you know, for any kind of rehabilitation, the more often you can provide the rehabilitation and the earlier on in the injury you can provide the rehabilitation will provide the best long-term outcomes. There's been a lot of recent improvements in technology that we kind of all have been discussing today. And a lot of these recent improvements in technology are now being incorporated into rehabilitation efforts. So motion capture, accelerometers, and gaming systems, which we've kind of already gone over. Some of the concerns associated with rehabilitation, again, I'm probably kind of preaching to the choir here, but time and cost. Home compliance is a big issue. In West Virginia in particular, we have a large rural population, and it makes it really difficult for these patients to travel to Morgantown, which is where the university hospital is, to get their treatment. So some of the possible solutions may be to implement a Kinect type system in a home for home rehabilitation or telehealth networking, and also to provide patients with interactive games that might help boost this home compliance issue. So again, like I mentioned before, possible ways to address some of these concerns, it really needs to be something that's easy to use and is low cost. We all kind of are facing this issue right now of insurance companies are getting stricter and stricter for what they want to pay. So cost associated concerns are really kind of at the forefront right now. So one idea we had was to kind of develop this wheel and spoke network, which basically would act as having a couple centralized physical therapists who could kind of monitor patients in real time in this kind of spoke-like system. So aim 3, this is a future direction we're kind of gearing up to get started right now, is to now take this automated system we've started studying in the lab and actually bring it into a clinical setting. Sorry that that's kind of cut off there. But what we would like to do is set up this system in a clinic and actually assess patients upon arrival prior to seeing the clinician. And so when the clinician actually goes in to meet with the patient, the clinician already has a printout of a score of the individual's motor impairment. We then want to record this information over visits and then examine these long-term outcomes from tracking their improvements over time. Aim 4, which is another future direction we are moving in the direction of now, is more of this home monitoring and rehabilitation system. So again, using this kind of wheel and spoke approach, we want to set up these Kinect-like systems in individuals' homes so they could actually do this rehabilitation while being monitored in real time by a physical therapist. We also want to provide them with some interactive games. And one idea we had too was to kind of, again, boost home compliance is maybe set up a network where these patients could actually play these games against each other. We all kind of know that competition drives a lot of things. So if we could give these individuals and these patients some competition through playing with each other through these online games, maybe that would help kind of boost their compliance. Okay, this is kind of a random little side note here, but recently our lab was visited by the Prime Minister of Healthcare from Estonia. So Estonia is a very small country, which I actually had no idea where it was even geographically located, but it's roughly almost the same population size as West Virginia, and they also have an extremely high rural population. So what Estonia, by the way, if you want to know one interesting fact about Estonia, that's where we got Skype from, so thank them for Skype. But what they have really moved to because of these high rural populations is that they are really now relying on telehealth care. So in these more rural communities, they're really relying on kind of this internet network to provide health care to their individuals. So we see this as kind of an interesting case study of hopefully eventually this is where we could kind of move to in the United States, providing patients with more in-home rehabilitation and therapy options. Kind of my last thing I always like to remark, especially when talking to clinicians, is the fact that we are not trying to replace physical therapists. We are simply trying to provide them with a tool that would help assist them do their job and provide better long-term outcomes to the patients. one of the comments we get a lot from physical therapists is, well, this system is going to put me out of a job. Physical therapists will never be out of a job. We all know that. You always need a person to be there and interact with the patient. We really just want to provide a tool that would kind of help alleviate a lot of the problems that they're having and the patients are having as well. So with that, I just want to acknowledge some members of my lab. My PI, Dr. Gritsenko, the postdoc in our lab, Dr. Talkington, as well as our lab tech who does a lot of the 3D programming for our virtual reality system, Brad Pollard. And our collaborator, Sergey Yakovenko, who works with us on our human projects as well as does some animal modeling for us, and then the funding of my fellowship. So that's all. I'll take questions. Yeah.
Is there a differentiation between the movements that you can naturally show the Kinect, like standing in one place, and some gait analysis that you can do? I mean, this would be restricted from the side of the Kinect, so I don't know what's the potential in the...
So you mean kind of the ability to use different types of kinematic data in this scoring algorithm, or?
Yeah, I mean, the Kinect is aiming like people who stand in one place and not people who are walking. So you would run into a wall, right?
Yeah.
It's a restriction of the device itself.
Right. Right.
Well, how does it connect with strokes in the analysis of different conditions?
So that's one other aspect that we really want to eventually get into, is trying to see if we can expand, maybe not this algorithm in particular, but an algorithm like it to kind of capture a broader range of neurological injuries that create these or cause motor impairments. As far as the clinical issue, so some of the concerns and things right off the bat we've had to address with putting this in a clinic is, first of all, you're going to have to be very specific as to where you set up the Kinect and where you instruct the patient to stand. Because we know there's kind of this sweet spot with the Kinect. If you're too close, it doesn't work. If you're too far away, it doesn't work. If you're moving a lot side to side, it might not work as well. Something else we have to think about is, what if we have an individual who comes in with a wheelchair? Is that now going to kind of interfere with the recording of the Kinect, or will it be able to pick it up as well? So we still have some room to improve, and some different tests we need to look at, and different patient populations we need to look at.
So the 17 trials of Wolf, the Wolf test do not include gait at all?
No, it's all upper body function.
Makes it easy.
It does make it easy. When you look at the upper body versus the lower body, obviously gait is nice to study because it's, in a healthy individual, is very symmetric, whereas the upper body you kind of have many more degrees of freedom you can kind of explore with your arms. But on the other hand of that, when you're just looking at upper body, you can have somebody be fairly stationary to assess their motor function of their upper body, whereas if you're looking at lower leg motor function, you need to kind of have them engaging a larger area of workspace.
The problem that I'm pointing at is that it's easier. The Kinect is targeting, and I mean it will be relatively easy to look at the upper body movement.
Mm-hmm.
But if you try to look at lower body movement, then you run into the device limitation.
Right.
So what I'm essentially asking is whether this is this going to limit you in your attempt to use home-based rehabilitation? So
as of the way the device and the algorithm sits right now, yes, we are limited to looking just at upper body function. I think there is absolutely room to improve on that, both on the technological and hardware and software side of things, as well as the algorithm we're using to look at upper body function may not be the best algorithm to look now at lower body function. So I think we need to kind of expand some of our research ideas to look at that. If we really want to integrate this in a home, it would make more sense that it could assess both lower and upper body function at once, not just one or the other.
Are you looking to collaborate with computer scientists on that?
Yeah. Always. So my PhD in particular is in neuroscience. I actually have a pretty strong background in physical therapy, though. My PI, Dr. Gritsenko, and our collaborator, Sergey, have been doing a lot of the kind of programming to take some of the SDK packages and develop them into these standalone systems. But as scientists, you always kind of run into this problem of you want to do a lot of things, but certain things take a lot of time. So if we had somebody who maybe was a little bit more geared on computer science side of things, we could probably develop and then test a lot of these algorithms a lot faster. So time constraints. Everything is time and money. Yeah.
So you said you're going to have this set up in a clinic where people will walk in. Are you going to have like a certain room for that, or are you just going to have it in the waiting room? And what do you expect the challenges that will be?
Yeah, so what our idea is to set up basically is to have this in a kind of a separate waiting room area where just one patient would go in at a time. And then you're going to eliminate a lot of the issues with people walking behind and opening doors. So the idea is that kind of the conceptual view we have right now is the patient would show up, they would check in, then a nurse would come and get them and escort them to this room. They would do the assessment. The nurse could either sit and wait in the room while they were doing it just to make sure there was no technical difficulties. And then as the patient was then waiting for the clinician to have their actual physical therapy appointment, the scores would kind of be sent or printed out so that the clinician could have those prior to seeing the patient.
And sorry, just to follow up. So just from a usability standpoint, do you plan to have any sort of survey questions or interview questions, or have somebody observe them to see what their experience was like and if they find it intrusive or weird? Or, you know?
Yeah. So we need to do a lot of investigation into how patients are going to perceive this, but also what we would like to do is kind of expand it so this could also be a type of survey and motor assessment system. So when they show up, they could have questions to answer first, like, well, what is your average pain on a daily basis? Are you having trouble navigating through your home? Have you fallen recently? Those kinds of things. So we could kind of build in some extra information into this generalized assessment. Yeah.
I wasn't quite sure of this algorithm that you used to create the score from the Kinect. So they came in and you did this wolf upper extremity battery.
Yeah.
Okay, and that's got a score to it. But then you had said you had this algorithm that the Kinect did the same score, or what was the algorithm that the Kinect, the automatic, how did it arrive at its?
Right. Okay. So what we do is we have the physical therapy students rate our subjects. Once we collect the kinematic data from the Kinect, well, I'm going the wrong way. We calculate joint angles, and then we use that information to then extract the principal components for it. So right now, this is all done kind of post-analysis in MATLAB. And that's one of the other areas we need to kind of focus on, is to make this, make all of those analysis scripts automated into the eventual software that will work with that hardware.
Can you describe
Sure.
I didn't quite understand the PCA. So you're doing PCA on shoulder abduction and shoulder flexion extension, all 4 degrees of freedom for
So we
and then
take
you're pulling out 2 principal components.
because if we pulled out 4 principal components, we would probably get the exact 4 angles that we were getting from the unaffected arm. So we're looking for the 2 principal components that are explaining the most amount of variance in all 4 angles.
And then I guess the piece I'm missing is the rationale for then using those. I didn't quite understand the leap then to applying those to the paretic arm.
Okay.
And what that shows you.
So
when
when we extract the principal components, we're assuming that these 2 principal components, and based on basically the mathematics used to do this decomposition analysis, that these 2 principal components are representing the most amount of variance from those 4 joint angles. So when we take those 2 components and then we reconstruct affected arm data, We want to see if there's a high correlation between the reconstructed data and the original recorded data. Then we know that the two limbs were moving fairly similar.
So it's kind of like your deviation.
Yeah, and if we can't reconstruct the data well for the paretic arm, then we know that there was a large difference in motor function between the two limbs, because now the variance that is explained for the unaffected limb is no longer explaining the variance for the affected limb.
And then that error is where what you calculate.
To get the score. Yeah.
Think of easier ways to compute the error. It's kind of.
Let me just
Sure.
try to understand that. So basically, what you're trying to measure is kind of the amount of symmetry between the two
Yeah.
arms, right? So,
Yeah.
so it's not as if you're saying that there is a right way to perform this act.
Correct.
You're just saying,
We're looking at the similarity of movement between the two limbs. Yeah.
So it's like in Gait, we can compare to this database of
Yes.
unimpaired individuals.
Yeah.
But here, everyone's going to do it slightly differently. So you compare to their non-paretic side.
Right, to their unaffected arm.
and you mentioned in your talk you had when you measured the accuracy of angle compared to the. What would be kind of what would be good accuracy? What can you
0% difference.
say? Yeah, that's easy.
Again, I think maybe, I mean, obviously if you're having on average a 50% difference between a state-of-the-art system in a low-cost system like the Kinect, that's going to raise a lot of red flags as to how well your motion capture is actually working. I think what maybe is, though, more important than the percentage is how consistent that difference is. And that really may speak more towards how the points of rotation are being actually calculated by the Kinect and the actual skeleton fit of the Kinect. So as long as that difference between face space and Kinect joint angles is pretty consistent, then it's just basically a built-in difference into how those joint angles are being calculated.
So is it fair to say that what you experience is more of a bias than a variance issue? So there's kind of a bias.
Yeah,
constant
I
bias
guess,
between
yeah,
numbers.
that would be a good way to describe it, yeah.
So what quantitative and qualitative measures did you get from Kinect, using Kinect?
So the quantitative measures are these. So basically this quantitative score. And since we're using correlation coefficients, it's a 0 to 1. It's basically an R-squared value that we're getting that when we're comparing those two reconstructed and original joint angles.
So let's thank Ryan again
Thanks.
for this.